In this video, I will be discussing the theoretical probabilities and the probability distribution for rolling a pair of fair dice. Now, let me remind you of what a distribution is. And distributions are often used in statistics to calculate probabilities for particular variables. And so distributions are of a variable. So when we think about distributions, we want to be thinking about what variable they're representing. They give all the possible values of that variable, and they also give the frequencies or the relative frequencies for the possible values. Now here I have a frequency plot for the distribution of a single fair die. I'm going to go back and review that. And I'm drawing a different graph here, a different type of a frequency plot than I did in the previous lecture on this. And this is a relative frequency plot. And notice up here I have 1/6, and across the horizontal axis I have the numbers 1 through 6. And each of these vertical lines represents the height, or this is how we often write these or display these distributions. And notice as soon as I start talking, my vertical lines start getting wobbly, so I stopped. But in any case, so that's a rough sketch. And so again, notice this is a representation of the distribution because we have the possible values here across the horizontal. The variable is number of pips, and the relative frequencies are all 1/6. And that's why we call it a uniform distribution. We can also display the same distribution using a table. And notice it gives all the relative information. It's of a variable, number of pips. Here are the possible values. Here are the frequencies, or in this case, relative frequencies with which all those values of the variable occur. Now, one of the ways that we can analyze these distributions is by thinking about the set of all possibilities, or what we call the sample space in statistics. So statistics is all about sampling. And so if we have a single die that we're rolling, then the sample space would be the numbers 1 through 6, if it's a 6-sided die. Whoops, let me write that correctly. So this would be the numbers 1 through 6. 1, 2, 3, 4, 5, and 6. If we're rolling a pair of dice, and we're summing, and the variable here is sum of the pips, then we could write the sample space as the set 2 through 12. And the idea here being that the lowest number we could roll is a 2, and that would be rolling a 1 on one dice and a die and a 1 on the other, or a 3 or 4 up to a 12, which would be 6s on both dice. Now, the way I've written the sample space here, it's a bit deceiving. If you didn't, without a deeper understanding of how these numbers are generated in the distribution, one might be tempted to see this also as a uniform distribution. So in the case of rolling a pair of dice, as in the game of Catan, which is a nice example because the dice in Catan are different colors, so we can think of them as individuals and think about what happens on each roll. Now, as we're thinking about the sample space, one thing to keep in mind is that we've got two dice, so we got a red one, and on the red one we could roll a 1, a 2, a 3, a 4, a 5, or a 6. And on the yellow one, we could also roll a 1, a 2, a 3, a 4, a 5, or a 6. Now, if we roll a 1 on the red, we could also roll a 1 on the yellow, or we could roll a 2, or we could roll a 3, a 4, a 5, or a 6. Notice here the sum would be, in this situation, if it were a 1 and a 1, the sum would be 2, and here the sum would be 3, the sum would be 4, 5, 6, and 7. But notice if we roll a 2 first, then a 1, here we get a 3. So there's a couple of different ways to roll 3s. There's only one way to roll a 2. That has to be 1 on both dice. But there's a couple of different ways to roll a 3. Or there's at least a couple of ways to roll a 4. Notice if I roll a 3 and a 1, that's also a 4. So there's 3 ways to roll a 4. So when we're thinking about the sample space with the pair of die, it's more complex because we have to look at all these combinations. Now, one way to view all these combinations is by using something we call a matrix. So across this row, I've just listed all the possible rolls where the red roll would be a 1. Across this roll, I've written all the possible ways or outcomes where the roll on the red die is a 2. Okay, it took a few minutes to draw all that out, but I think it's worth it because now you can see pictorially or visually all the different possible combinations. And instead of there being 11 possibilities, there are actually 36 possible rolls that can happen. And so writing the sample space in this way allows us to see all these different combinations. So here's our 2 roll, a 1 and a 1, the 3 roll, the 3 roll, 4, 4, 4. So along each of these diagonals this way, we can see how many each of those rolls can be done, or how many ways each of those things can happen. So a 5 would be a 1 and a 4, a 2 and a 3, 3 and a 2, 4 and a 1. So there's 1, 2, 3, 4 ways that could happen. Or I'm sorry, is that right? 1, 2, 3, 4. Yeah, 1, 2, 3 ways. to roll a 4, 2 ways to roll a 3, 1 way to roll a 2, 4 ways to roll a 5, and so forth all the way across. And then down here we have 12, 11, and 10. And then, of course, the 7, 6 and a 1, 5 and a 2, 4 and a 3, 3 and a 4, 2 and a 5, and 1 and a 6 is the easiest roll. So if we start to think in terms of probabilities, the probability of rolling, say, a 2, and again, I'm using some probability theory kind of notation, would be 1/36 because there's one way to roll a 2 out of 36 possibilities. There's 6 possibilities here, 6 possibilities here for a total of 36. And I could also calculate the probability of rolling another number, like the probability, say, of rolling, let's just say 7. Probability of rolling 7 would be, well, I would count the number of ways that a 7 could be rolled. 1, 2, 3, 4, 5, 6 ways. So that probability would be 6 out of 36, which simplifies to 1 out of 1/6. So here's the table now that I asked you to complete on one of the activities. And so I want to go through this and show you how you could calculate these what I'm calling theoretical probabilities. So here's the relative frequency of 2's. And again, we use the words relative frequencies and probabilities interchangeably because in statistics, we think about probabilities as the probabilities as relative frequencies. So I started the table off with a few examples. So this 1/18 is actually, you should think about this as 2/36 because there's 2 ways to roll a 3 out of 36 possibilities. This would be 3 out of 36. Now for rolling a 5, there's 4 ways to roll a 5. So there would be, this probability would be 4 out of 36, which would simplify to 1/9. And then rolling a 6, there's 5 ways, so that's going to be 5 out of 36. That fraction doesn't simplify. For 7, we already did that, 1 out of 36, or I'm sorry, 6 out of 36, which simplifies to 1/6. Now the interesting thing is the numbers start going back down sequentially here because there's symmetry. There are 5 ways to roll a 6. That would be a 1 and a 5, a 2 and a 4, a 3 and a 3, which incidentally in the game of craps we would call a hard way because there's only one way to roll a pair of 3s. So the hard 6 in craps is a 3 and a 3. In any case, so we have, let me go back for a second here. We got a 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2, and a 5 and a 1. With an 8, we could roll a 2 and a 6, a 2 and a 6, a 3 and a 5, a 4 and a 4. That's the hard way for an 8. A 5 and a 3, a 6 and a 2. So I think I counted them all up. There's 5 ways out of a possible total of 36. We can do the same one for the same reasoning for a 9, 10, whoops, that's 3 out of 36 up here. Let me make sure I get that right. Let's see, 2 ways to roll an 11, 1 way to roll a 12. And so this would be one way to display the probability distribution for the outcomes of rolling a pair of fair dice. I hope you find this video helpful, and I'll see you next time.